signal proportional to the magnitude of the error signal. Unfortunately, the closer you get to the set point, the less it pushes. Eventually, the process just runs continuously close to the set point, but not quite there. That's when integral jumps in. The integral block creates an output proportional to the duration and magnitude of the error signal. The longer the error and the greater the amount, the larger the integral output. As long as an error exists, integral action will continue. The derivative block creates an output signal proportional to the rate of change of the error signal. The faster the error changes, the larger the derivative output. Derivative control looks ahead to see what the error will be in the future and contributes to the controller output accordingly. That brings us to a term called controller tuning. We said earlier that every process responds differently and that the PID controller determines how much and how quickly correction is applied by adjusting proportional, integral, and derivative action. Controller tuning involves correctly setting the controller P, I, and D values for specific process requirements. Interestingly, the correct settings achieved by controller tuning can differ vastly between processes because of specific requirements. For example, after the controller has been tuned, a set point bump of 1% at a tank level control produces a quarter wave damped response. This type of response may be suitable in a tank level process, but could be disastrous in a motion control process. There are many different manual methods for tuning a controller that involves observing the process response after inflicting controller set point changes. One method involves increasing the amount of set point change and repeating the procedure until the process enters a state of steady state oscillation. This method of tuning produces adequate results, but is often impractical in many applications. For example, how practical is it to force the fluid level in a large tank to reach a steady state oscillation? Most process controllers, PLC, and DCS loop controllers sold today have auto-tuning capability. The PID controller learns how the process responds to a change in set point and suggested PID settings. Regardless of whether the initial PID parameters are derived from the manual or auto-tuning methods, additional tweaking is often required by seasoned automation professionals to get the response desired. That should do it for this video. If you want to learn more about PID control, you might want to watch our other two videos called What are PID Tuning Parameters? And How to Tune a PID Controller. You can find the links to these videos in the description. Okay.
This is how to get in shape fast.
The best way to boost your metabolic rate and get in shape is not keto.
This video is part of a free course. If you want to learn more about PID controllers in an easy-to-follow format, head on over to realpars.com, where you can sign up for this course, as well as several other courses on PLC programming and other topics related to industrial automation and robotics for free. You can find the link in the video description as well. In this video, we're going to look at the effects of proportional-only action on a flow control loop. Proportional-only control is the simplest of the PID controller actions, but is seldom used in industrial production processes. The problem with P-only control is something called offset. In this video, we're going to explain offset and show you how and when it occurs. The controller in our loop is typical of most controllers. We can adjust the set point and switch between auto and manual. In manual control, we can adjust the controller output to the exact amount we want. Our flow loop has a pump to move our process fluid. We can turn the pump on or off, which will be very helpful for observing PID responses in static and dynamic conditions. Okay, let's kick things off with a look at our flow control loop P&ID. The flow is manipulated by the pneumatic final actuator, FCV200. The controller FRC200 produces an electrical signal that operates the pneumatic final actuator through a current to pressure, or I to P converter, FY200. The differential pressure transmitter, FT200, sends an electrical signal representing the flow rate to the controller. And now, let's look at an animation of the flow loop in operation. Okay, let's start investigating the effects of adjusting the amount of proportional action on our flow loop. The controller output range is 4 to 20 milliamps, representing 0 to 100%. When the process is stable, the controller output will be at some value between 4 to 20 milliamps.
So I don't think I went over this sensor type. Have I gone over the 4 to 20 milliamp sensor before in this class? Okay. So as we discussed before, many sensors, particularly ones that are really, really local to us, like on the circuit board that our microcontroller is also on, or over a very, very short length of wire, we use voltage to show. Come on. I was just writing. What happened? There must be something weird on this board. There we go. Okay. Please. Okay. So for example, temperature sensor, or rather temperature sensor and voltage. Where if we have a temperature sensor, as there is some relationship, more or less linear, between, at this temperature, say 80 degrees Celsius, there is some voltage that will come out. So if we have a 3.3 volt supply, then this might be like 2.8 volts, okay, like on the upper side of its readout or whatever. So similarly, this is like given to us by the manufacturer. That we might also know that, down here at like 1.8 volts, that this means things are 25 degrees Celsius. And then anywhere along this range, we more or less can figure out what voltage is between what temperature, right? If this was perfectly linear, it would be really easy to tell, right? It would just be a simple y equals mx plus b. You could figure out for a given voltage, we could figure out what temperature we're seeing from that sensor. Okay. However, over long periods of time, over long distances, rather, if I have my little sensor over here and I have voltage running on this line and that guy's connected to my PLC all the way over here, voltage droops over this line, all right? If you took a multimeter and I tried to measure what does this signal look like, I might get that 2.8 volts. If it's 25 degrees C in the room that I'm in, and I read 2.8 volts, I know that that's 25 C, that's what I expect, right? But say if I had this temperature sensor on too long of a lead, my voltage starts to droop, okay? So if my PLC is all the way over here and not like, a 1-inch wire, say it's a 1-mile wire, the voltage that I'm seeing might be like really low, like 1.5 volts. Okay, the sensor is sending 2.8 volts, but there's resistance over this line such that I'm only seeing 1.5. Okay, that's a problem. Because if this PLC sees 1.5, it doesn't think that it's 25 degrees, it thinks it's much less. And that's an error coming in, right? Our input isn't what it actually is. So this is problematic. We want to make sure that our sensors are reporting things to us in a way that won't be degraded by the environment, right? Interference can mess with this, the drop of the line can mess with this, all kinds of stuff. However, if we use current instead, okay, so instead of voltage, if we use current, this is still temperature, things change, okay? So what they've done is they've standardized this distance. Sorry for these markers. Can I just move to like a different spot? Okay. All right, so they developed a 4 to 20 milliamp standard. Okay, so rather than like 0 volts to, whatever your source voltage is, 3.3 volts, no matter what, it's 4 to 20 milliamps. So for example, if my sensor went from 0 degrees to 100 degrees, if my PLC saw 4 milliamps coming out of that sensor, we would know it's 0 degrees. If we saw 20 milliamps come out of the sensor, we would know it's 100 degrees, okay? I won't get too into why this works, but the main thing is that the amount of current that flows through here, this line could be really, really long, and we can still figure out what we need to send through it to get given current. Okay, they make these things called constant current sources. Anyway, we can much better transmit this information, how much current there is rather than how much voltage is, in order to get information. Okay, so all that to say, the sensor that they're using in this particular example doesn't report in voltage. It reports in current that we're digitizing into our PLC, and that means something. In this particular case, a flow rate. So when we get 4 milliamps, we know that we're getting a flow rate of 0. And if we get 20 milliamps, we know we're getting a flow rate of 100%, the maximum that can flow through the pipe. The reason why this isn't 0 milliamps is because of fault tolerance. If we see 0 milliamps coming in on what should be at least 4 milliamps in all possible scenarios, we know that there's a break in the line. It's fault detection. Okay, it's industrial ruggedness in play. Okay, so that's why it's also not 3 or 2, because that's kind of like borderline 0. There's a really clear difference between 4 milliamps and absolutely 0 if the line was cut. Okay. So that's why this range, any more than 20 would be just like passing energy. We're not actually usually powering anything with this current. It's just information. How much current is flowing through here is like a data point rather than like energy transmission. Okay. Any questions on that? That a little more clear? Okay.
The process variable is also represented by a 4 to 20 milliamp signal from the flow transmitter. This signal represents 0 to 100% of the process variable. All right, now that we know how the flow loop operates, let's move on to proportional control. So what is proportional action? The controller's job is to ensure that the process variable is the same as the set point. The controller is always looking at the difference between the set point and the process variable. This difference is often referred to as the error. Proportional action is an amplification of the error. This proportional amplification has no units and often is referred to as gain. This amplified result is added to the current controller output. Okay, now we have a simple math formula. New controller output equals previous controller output plus gain multiplied by error. Let's look at an example of proportional action and how that math formula applies. We'll start with the pump off. With the controller on manual, we'll set the output to 50%. We'll set the gain to 1. Now, let's set the controller to auto. With the pump off, the PV, or process variable, will be 0. Watch what happens when we change the set point from 0% to 10%. The set point change of 10% produced a 10% change in controller output. Why? The controller output, or CO, changed by 10% from 50% to 60%. Earlier, we said that proportional action results in a change in controller output based on the simple math formula. Controller output equals CO plus gain multiplied by error. Our set point changed from 0 to 10%, which produces an error of 10%. The gain is set to 1. Because the gain is 1, the proportional action will only add 10% to the controller output. The controller output was at 50%, so adding the proportional response will move it to 60%. Let's try it again, but this time we will increase the gain to 2. This time the CO changed from 50% to 70%, which is a 20% change. Why? Because the gain is now set at 2. Therefore, the proportional action will add 20% to the controller output. Keep in mind that the pump has been off for both of our experiments. With the pump off, we have no possible change in the process variable. Therefore, our proportional action is acting on a static condition. Once the pump starts, we are in a dynamic environment, and variables are changing with time. Let's turn the pump on and watch the proportional action dynamic response. We start with the process variable at the set point value of 75%. When we introduce a set point change to 65%, the controller initiates proportional action and attempts to change the process variable to move to 65%. But the process variable only goes to 69% and stays there.
Introducing the new EcoPower Plus 2-stage snowblower, a heavy-duty workhorse with unmatched power.
A proportional-only controller does the job expected of it, at least until a disturbance, process variable, or set point change happens. In the beginning, the process variable equals the set point, and the error is 0. The process variable is stable. A process disturbance will cause the process variable to change, and the controller will act. Unfortunately, the process will recover back to a condition of stability, but not with the process variable at the set point. The difference between process variable and set point is called offset, and occurs in proportional-only controllers. In our next video, we'll show you how adding integral action will help bring the process variable back to the set point, thus eliminating the offset. If you want to learn more, you might want to review our other videos called PID Controller Explained, How to Tune a PID Controller, and what are... This video is brought to you by us, RealPars. This video is...
Sorry, hold on. I was hoping it would be right there in the... I'm going to have all of these online or in the presentation, so you can go back to this channel if you wish. But last time they were all in the sidebar, so apologies. Hold on. Proportional only. Oh, nice. All right, so 2 more videos of this guy.
PID is an acronym for proportional, integral, and derivative.
Integral.
The controller is a device that is used to control a process. The controller can be a physical standalone device, or a control block found in a PLC function database. The PID portion of the controller is a series of numbers that are used as adjustments in order to achieve your objective. Before we get started on today's video, if you love our videos, be sure to click the like to see notifications of new real. A very simple example of a PID controller would be the regulation of a heating and air conditioning system in a home. Although there is a lot more to the controller than this example, this will give you a basic idea of the purpose of a device like this. Say you have the temperature in your home set to 70 degrees Fahrenheit. The setting would be called the set point, or SP for short. The current reading from the thermostat is 68 degrees. This term is the process variable, or PV. The heating or cooling unit is the control variable, or CV. The control variable may also be referred to as the manipulated variable, or MV. There are different types of control action, and for the temperature control in the house, the controller action is a direct acting device, meaning that the calculations are set point minus process variable. In our house example, we have a set point of 70, and the process variable is 68. For this control, when we subtract the process variable from the set point, we see that we have a value of 2. The result is called the error, or E in our process. In the simplest terms, our house is too cool, and the controller tells the heating unit to turn on. Remember, we're trying to get to 70 degrees. The unit will remain on until the error in our process becomes 0. Now, let's say that someone opens a window in the house, and it's very cold outside. This disruption in the process is called disturbance. The factors in this process control may be How fast do we want the temperature to reach the set point? And what could disturb our process? Clearly, there are many factors that can impact our processes, and adjusting our controller's parameters is how we deal with those factors. Another example of a slightly more complicated control process, for understanding purposes, would be you changing lanes while driving. You would be the controller. The lane that you want to be in is your set point. The steering wheel would be your control variable, and your current position on the road would be your process variable. Your eyes are your feedback. You adjust your steering wheel according to many factors, such as the angle of your wheels, possible wind disturbance, the position of other vehicles, that sort of thing. You don't do hundreds of calculations to determine your point of attack. You intuitively, after years of driving, know what you need to do to safely switch lanes. Because you are not blindfolded when you drive, your eyes give feedback to your brain, allowing you to control this process through reference feedback. This control is considered a closed-loop process. But consider a blindfold. You'd have no way of knowing where you are on the road. This type of control would be called open-loop control. Obviously a much more difficult process to control, and on occasion, you may run into this type of control in your career. In an industrial plant, since there are many factors that we need to consider, we need a robust controller that takes our parameters into account and does hundreds of calculations to determine where the process is and where it needs to go. Say we need to control gas flow through a pipe. The set point of gas flow is calculated based on a calculation of some factors. This set point can change at any time based on the parameters used in the calculation. We will control this flow based on a modulating valve. In this case, the more open the valve, the more gas allowed to flow. The requested position of the valve is our control variable. Downstream of this modulating valve, we have a flow meter that will measure the gas flowing through the pipe. This is our feedback, or our process variable. In this example, we are going to use a PLC function block in order to control this process. Our PID block will be able to use the parameters we specify to determine the controller's reaction to our process. Let's take a step back and talk about the parameters that we will be adjusting for our control. First, the PID term, as stated earlier, stands for proportional, integral, and derivative. These parameters can be used individually or collectively, meaning you can have just a proportional controller, a proportional and integral, a proportional and derivative, or of course, a proportional, integral, and derivative controller. Each of these parameters is enabled and adjusted individually, and each controller type would be used for specific purposes, each parameter having a specific impact on the way the controller functions. To sum it all up, we, as control engineers, need to control processes, and in order to do that, we use devices available to us in order to facilitate that function. The standalone and integrated PID controller is the most widely used device for that purpose. In our next video...
All right, so we're gonna do one more video that's just gonna kind of show you the different types of examples in industry, and then we'll take a small break and then we'll continue on the lecture.
At Capital One, we start with applied research, leveraging our data to build models and embed.
This video is sponsored by RealPAR's business membership. And finally, a new video, wheel.com/business. Please fill out the form. In this video, we will discuss PID controllers, what they are and what they do, their evolution to modern-day industrial applications, and finally, a few newer control approaches. A PID controller's purpose is to maintain a process variable at a desired set point automatically. How is this accomplished? In a control loop, a process variable is constantly being measured and compared against a desired set point, which a human operator usually establishes. Suppose a difference exists between the measured value and the desired set point value. In that case, corrective action will occur on a manipulated variable to bring the process variable closer to the set point. Sounds easy enough, huh? We'll apply this concept to the interior temperature control of a car. Let's say you're rolling along the highway when the outside temperature changes, causing the interior temperature to drop. The new cabin temperature is sensed, fed back to the controller, and compared with the desired set point temperature. The controller will move dampers or valves, mixing outside air with engine heated air to increase the cabin temperature until it reaches the set point. Are the dampers opened fully? Are they throttled? How quickly do they move? That's where the P, I, and D of PID control become essential. We don't want the cabin temperature to increase past the set point or too slowly. Obviously, damper movement is critical. The PID algorithm determines the control action. P stands for proportional, I stands for integral, and D stands for derivative. Adjusting these parameters changes how the controller responds. Proportional looks at the current value and provides an adjustment based on its difference from the set point. This difference is referred to as the error. Integral looks at the changing error, and derivative tries to predict where it is going. The P and I terms tell the corrective action to keep going. Derivative catches the corrective action and says, "You're going too fast. You need to slow down." In this video, we're not attempting to teach you about PID theory. If you're interested, check out our PID Controller Basics course, linked in the description of this video. Many automation and control folks credit Elmer Sperry for inventing the simple feedback PID controller in 1911. Elmer created a system to control a ship's rudders to help prevent it from sinking due to waves and other external forces. The first practical industrial PID controllers emerged in the 1940s, such as the Foxborough 43P pneumatic controller. The introduction of electronic PID controllers, such as the Foxborough Spec 230SM control station, led to the widespread use of PID control in process industries. Control rooms were filled with single-station controllers mounted on panels, each managing one process variable or control loop. A piping and instrumentation drawing, also known as P and ID, shows how equipment, valves, and instruments are connected in a process. A discrete standalone level indicating controller, or LIC, located on a control panel and accessible by an operator, is displayed using a circle with a device tag number printed inside. Single-station controllers have all but disappeared from industry. Today, we have PLCs and DCS platforms that are capable of managing multiple processes via centralized control, resulting in faster data processing and analysis. For example, the AB Control Logic's PLC 1756-IF8 analog input module can receive process measurement data from up to 8 separate processes. PID control is managed via the RS Logic's 5000 programming language, or the newer version Studio 5000 Logic's Designer. A DCS is a computerized control system with multiple autonomous controllers that operate and control many control loops. Field devices are connected to controllers with multiple I/O modules located in cabinets. The controllers are networked using many communication protocols, such as Ethernet or Modbus. Operator station HMIs are located in a centralized control room. The operator station allows plant operators to observe and adjust real-time plant conditions. An engineering station HMI is located in an area only accessible for actual control logic programming changes for any of the many control loops. Here's an example of a Yokogawa Centum VP HMI display. The level indicator controller, or LIC 501, is set to manual mode and currently shows a reading of 0%. The controller's output operates a valve XV522. How is a DCS controller shown on a PNID? We draw a square box around the discrete standalone symbol to indicate a DCS controller. A simplified PNID from our Yokogawa example shows the level controller and the valve XV522. Of course, not all DCS HMIs have the same appearance. Controllers on the Foxborough IA DCS HMI are designed to resemble the face of a traditional single-station controller. PID controllers are used.
So just a small point.
Not all and the valve.
Again, talking about like what the actual job might entail when it comes with PLC controllers and like what the reality would be, very possibly upon, hiring or being told what you're overseeing, you'll be given many pages like this, and you'll be shown a control panel that you said is connected to many PLCs. The HMIs that they were talking about is human machine interfaces. Okay, so keyboards, mice, displays, things like that. All of that will be in like a central location. PLCs may or may not be elsewhere. And then they'll give you your terminal that you can use to access the PLC or IDE, just like we're doing here. And then they'll give you the process diagram and they'll say, here's your PLC. These are the processes it's hooked up to. These are the instruments it talks to. And here's the program and the user interface. And that'll kind of be it. And then you guys would be responsible for going, okay, I know what these symbols mean. I know how it's wired up. I know what it needs to do and how to access the device and all that stuff. It kind of becomes the practical in the situation. Okay.
XV522. Of course, not all DCS HMIs have the same appearance. Controllers on a Foxborough IA DCS HMI are designed to resemble the face of a traditional single-station controller. PID controllers are used in almost all industries to control various process variables. To name a few, temperature controllers are used in manufacturing to ensure precise temperature management, such as in food production and chemical processing. Flow controllers manage the flow of oil, gas, and steam in pipelines, refining operations, and other production processes in the oil and gas industry. Pressure controllers are used in petrochemical processing to manage pressures in distillation columns and separators. Level controllers are often found in chemical processing plants. They are typically used to maintain liquid levels in tanks and vessels within a specific range. Acceptable responses to set point changes or disturbances differ depending on the application. For example, a quarter-wave damped response may be acceptable in a level control loop, but disastrous in a motion control system. In a motion control system, the actual position must closely follow the target or set point position. Attaining the desired response is where the flexibility of PID control truly stands out. Control loop tuning is adjusting the P, I, and D parameters to achieve optimal performance. There are lots of controller tuning methods. Engineering students are familiar with traditional tuning methods, such as Ziegler-Nichols, Cohen-Kuhn, and reaction rate methods. The disadvantage of traditional tuning methods is the system upset requirement to obtain valuable process response data. For example, the Ziegler-Nichols method requires the process to be placed in a state of constant oscillation, which can be impractical or dangerous. DCS controllers often have built-in algorithms that automatically adjust PID parameters without nasty system disruptions. Whatever tuning method is used, final tweaks by seasoned professionals are often required to fine-tune the system. Hopefully, we haven't given you the impression that PID controllers are the only choice for process control in the industry. Other control methods include fuzzy logic control, or FLC, and model predictive control, or MPC. PID controllers are the most common because of their familiarity and functionality. FLC is suitable where human input or linguistic variables are involved, such as consumer appliances. MPC works well in systems with multiple interacting variables, such as industrial processes, robotics, and autonomous vehicles. Alright, that wraps up this video. We hope you enjoyed it and found it helpful.
Okay, so hopefully that clears up the vocab for you guys a little bit, and you now understand or can recognize PID controllers and what they do and what they are. That was the goal for today. We're going to take a 5-minute break, cool off, get a drink, come back. We'll at 7:30, 5 minutes from now, or 7:32, depending on the clock. Yeah, 7:32 on my clock, and we'll get back at it. Okay? All right.